Thanks very much, Andis. Yeah, it's great to be here, to be invited to be here, and to see you all and to discuss with you all. It's you're a very enthusiastic group and very willing to learn, and it's great to see. I'm a little bit older. I was also very young when I started. No, not that young, but and it's always great. You are very enthusiastic. You have ambition, and it's nice to see you all have that ambition. And the talks I saw yesterday, they were great. The ideas. So I'm very enthusiastic to be here, and hope to see you more often at the meetings. And fortunately, this is the first for me face to face, and I hope there will come more. Okay, I have the opportunity to tell you something about the future of Hodgkin's therapy in childhood and adolescence. It's a very broad title, but and you can think about it. And I gave my interpretation of the title, and you will see how I will move on. First of all, I would like to thank my colleague and co-worker, is Friederike Meijer-Wentrup. She's working also at my department, at our department in the Maxima, and she provided me with some important slides. Feel free to interrupt, to ask questions and to raise your hand, and then I'll try to answer the questions. That's no problem for me. And halfway my talk, I have a question for you, just to get you awake a little bit more then. But we'll see. Yeah, the future, but when you say about future, do we need more chemotherapy? Do we need other chemotherapy? Do we need more radiotherapy? What you want is to cure the patients, of course. And fortunately, in Hodgkin's disease, curation is very good. So what we have, what kind of drugs we have, they do very well, and nearly all patients are cured. Still, so EFS of 85 to 90% and an overall survival of 95% means that there are still patients who relapse or even die. And for instance, if you look at high-risk groups, then you have the patients who have not DOVL 4 of DOVL 1 to 3, but DOVL 4 and even DOVL 5. And those patients have a very low EFS comparing to all other patients. So then you say maybe you have an EFS of 70%. So they will relapse. So maybe also in first line treatment is necessary, especially for those groups. And when we look at relapse treatment, you see the table on the bottom, a lot of chemotherapy, conventional standard chemotherapy, and you see that although not all are crowded with patients, still you can say something about the overall response rate and also the CR rate, and they are not 100%. So we need new drugs, considering that. The other thing is toxicity. You have early toxicity and also late toxicity, and we already discussed a little bit this morning. Fertility is an important problem, not a problem, an important thing to consider. Heart failure, but also secondary malignancies. And as you see in the pictures below, in secondary malignancies, you find them 27% in breast cancer, and most of the patients have Hodgkin's disease as original diagnosis. So probably we need new drugs, I think. So more effective drugs we need with less toxicity and also maybe less radiotherapy as well to reduce the toxicity, at least the late toxicity. When you want to find new drugs, you have to know what cancer is, and maybe you're all aware of this very nice paper in Cell by Hanahan and Weinberg, and a revision later on. And it's very important to know what kind of cancer you're dealing with. And maybe the last two, the avoiding immune destruction and also tumor promoting inflammation, these are areas where targets for immunotherapy can be found. And how is Hodgkin disease shown? What we know about Hodgkin is that only 0.1 to 10% of the lymph nodes or the disease is occupied by Hodgkin cells or Reed-Sternberg cells. So a lot of other cells are there, so-called microenvironment. Now HRS cells as a B-cell origin. Yesterday, Anjish asked us about it, but you can't see the B-cell characteristics on the surface membrane, but well, but you can see it in the molecular way. HRS cells produce cyto and chemokines to maintain that inflammatory microenvironment. So maybe we can check the inflammatory environment and try to hit them, and then the Hodgkin cell has problems. Now, the microenvironment consists of activated T cells, tumor-associated macrophages, eosinophils, and fibroblasts. Very important for survival and proliferation of the HRS cells. And those serum biomarkers, which are produced, can be found in the serum too, and can be also be a diagnostic marker or a response marker. Maybe you have known of you have heard already of TARC. It's a very important marker, and unfortunately, I do a lot of research in TARC. Not all Hodgkin patients have TARC positivity. That depends a little bit on the amount of Hodgkin cells, but also not all of. There are some other mediastinal enlarged tumors, so it's primary mediastinal B-cell lymphoma can also have high TARC. So it's a very nice diagnosticum, and also you can use it for response measurements, but it's not 100%. It's not a black and white phenomenon. Okay, the immune system, I'll come back to that, recognizes tumors, and that is because cancer cells have non-self characteristics through expression of mutated proteins. Patient-derived immune cells can recognize and kill tumor cells, but it's needed by priming by antigen-presenting cells, presentation of peptides in the right MHC context on the tumor cell surface. And also an immune stimulatory microenvironment are prerequisites for acquired anti-tumor immunity. So there is something needed when you try to target the immune system. The key players in the immune system are listed here, so dendritic cells, B cells and macrophages as antigen-presenting cells, and the effector cells are T cells, B cells for antibody production, and the NK cells. When you look at the tumor and the immune system, these are in interaction. And you have the 3 E's: elimination, equilibrium, and escape. So when there is elimination, then the immune system can kill the tumor cells who arise in an organ, for instance. When there is an equilibrium, then you see that the tumor cells are killed, but not all, but it's sufficient enough to have a sort of steady state and no real problem. But when the tumor cells can escape, then you have a problem, of course. And that's depending also on genetic instability, tumor heterogeneity, and immune selection, of course. It's more shown in a graph, and you see here in that tumorigenesis starts to develop, and you see here 2 kinds of cells. So a highly immunogenic tumor cell and a poorly immunogenic tumor cell. And when there is a highly immunogenic tumor cell, it will be recognized by the immune system and probably will eliminate it. But when there are more and more poorly immunogenic tumor cells, so what we see in children with less mutagenesis, then immunoediting will develop and the tumor will stay. And eventually immunosuppression will start. It's what we see in Hodgkin's disease, and I'll come back to that later, and then escape, and you have a tumor. What is immune therapy? And the NCI says it's using the immune system to treat cancer. And there are modalities, of course. I will come back to that later. Immune checkpoint modulators, adoptive cell transfer, therapeutic antibodies, cancer vaccines, and immune system modulators. And I would like to show for a few minutes this film. You can find it on YouTube. It's about Steven Rosenberg, one of the founders of immunotherapy, just for inspiration.
Immunotherapy is a type of treatment that prompts a patient's own immune system to fight cancer. In this excerpt from the documentary film Cancer, the Emperor of All Maladies, Dr. Steven A. Rosenberg head of surgery at the National Cancer Institute's Center for Cancer Research, describes his pioneering work in this promising field. He begins by recalling an inspirational encounter early in his career with a patient whose cancer had disappeared without treatment.
All aspects of his cancer were gone. He had undergone one of the most rare events in all of medicine. He had had a spontaneous regression of all of his metastatic cancer.
Rosenberg believed that the explanation had to lie in the patient's own immune system. He decided then and there to focus his research on immune cells, or lymphocytes.
Okay, let's talk about admissions for this week. The body has hundreds of billions of lymphocytes. And somewhere in the body of a cancer patient, there are lymphocytes, we hypothesize, that could recognize what was different about the cancer. So Mark, let's hear about cells.
We have Cermak on the NMA arm of the randomized protocol. Let's do start diffusion.
It was that hypothesis, it was that dream that then led us to try to identify the actual cells that were attacking the cancer and use them to actually develop a cancer treatment.
Rosenberg isolated various types of immune cells in his lab, and in a series of clinical trials, injected them into patients. But progress was painfully slow. In the first 66 patients, his therapy showed no signs of working. Then, in 1984, he treated the 67th, a Navy officer named Linda Taylor, with a far higher dose. 3 decades later, she is still in perfect health.
Oh. I tell you, I never cry except around you.
It was an important event in the development of cancer treatments because it showed people that it was possible, at that point in a very tiny percentage of patients, to cause the immune system to make a cancer disappear.
The hope from those early experiments was that if you could somehow activate specific aspects of the immune system, could you now educate it to attack a cancer cell and not attack a normal cell?
Rosenberg went on to discover that a specific type of immune cell, called a T cell, was active against some cancers, but when greatly outnumbered, was too weak to defeat them. Through dozens of experimental trials, he learned to extract these cancer-fighting T cells from a patient's own body, grow them in the lab into a vast army, billions of cells strong, and then infuse them back into the patient's body to fight his or her cancer.
So in our last 6 evaluable patients, there are 4 complete regressions and 2 partial regressions. So that protocol.
We're in the beginnings of a very long and hopefully exciting road with immunological therapies. There are people who dedicated their lives to this. And finally, we're beginning to see interesting glimmers in which the immune system can be educated to start to see cancers and to kill those cancers.
I think it's an inspiring YouTube film, and he was the godfather of the immunotherapy, and so it's nice to see that and to honor him in this way also. I will go on, continue with it, and I think what's important is just I give you some examples of what kind of new drugs, new immunotherapy we have, and I'll come back to studies we have in Hodgkin's disease. Antibody-mediated versus cellular immunotherapy. So cellular, of course, we all know the allogeneic stem cell transplantation, which is a cellular immune therapy. The CAR T cells, the tumor-infiltrating lymphocytes, NK cell transfusions, vaccinations with dendritic cells, and also the antibody-mediated, this antibody against tumor antigen, I'll come back to it later, against the tumor microenvironment, so maybe what we can do in Hodgkin's disease, and also against checkpoint molecules. What are antibodies? Just a refreshment. Part of the gained immunity produced by B cells, of course. They are antigen specific. and you have too heavy into light chains when you look at IgG. There's a functional domain, it's this part of course, and the FC domain, which is there. What are the monoclonal antibodies? They recognize one epitope on the cell surface. It's very important. They are recombinant produced, can be obtained as a drug off the shelf, and are mostly humanized. And a very important example is, of course, rituximab. It's one of the first monoclonal antibodies developed, and already in 1997 got an FDA approval, so that is now 25 years ago. The first international trial, which was randomized between CHOP and R-CHOP, showed a better survival, EFS and overall survival in adult patients with a diffuse large B-cell lymphoma. It took us a lot of time to start with pediatric studies, unfortunately. And 2 studies are mentioned here. And it shows that rituximab is also valuable in our pediatric patients with a B-NHL. Brentuximab vedotin, that's also an antibody, but then an antibody-drug conjugate. That means that there is a drug bind through a linker to the antibody. So the antibody will recognize, in this case, CD30, which is an anti-CD30 monoclonal antibody. Then there will be endocytosis, where the drug plus monoclonal antibody is getting into the cell. Then there will be linkage to the lysosome, and at that time the linker will be broke down, and then the drug will come free and have its role in the cell itself, and the cell will die. There are 2 phase 2 trials then done, monotreatment, and what you see that's in Hodgkin lymphoma in adults is CR rate of 34%. So only one drug can kill the cancer cells, and in 34% you have a complete remission. And in ALCL it was even more, 57%. Toxicity is important, of course, and that's reversible by neuropathy, as vincristine has also, because it's a vincristine analog, the monomethyl orostatin A. You find it, but it's reversible. Another drug which is not used, of course, at this time in Hodgkin, but maybe it can later on, is blinatumomab, first developed in children and got an approval in 2017, and that's so-called BITE. So that means that it's a CD3 antigen plus the CD19 B-specific, and it will bring the T cell in the neighborhood of the malignant B cell and can then kill the malignant cell or get T cell proliferation and also kill the tumor cell. Then the next thing is the immune checkpoint blockade, and it was also a revolution, at least in the treatment of metastatic melanoma, and also of immunotherapy of cancer in adults. And the most known are the anti-PD-1, anti-PD-L1 drugs, and also anti-CTLA-4. And just for clarification, how does it work? And then you have to go back to the normal situation. When an antigen-presenting cell is presenting a peptide to a T cell, then there will be, with some co-stimulatory proteins, of course, then the T cell will be activated, and there will be cytokine production and cell cycle progression. And then a lot of inflammatory mediators will come and will kill bacteria. When that's not a sort of blockade system there, then the T cell will still go on, and then you can have autoimmunity. Now, what is done is that there are a sort of feedback loop mechanisms through PD-1 on the T cell and PD-L1 on the antigen-presenting cell, which tells the T cell to stop producing inflammatory cytokines. And a tumor cell, and at least also the Hodgkin cell, makes use of that. What it does is, what you see in the Hodgkin cell is a lot of mutational amplification phenomena of PD-L1, and in this case, it causes that the T cell, who can recognize the tumor cell as aberrant, will do nothing due to energy. And what is done with immune checkpoint inhibitors is that you block the PD-1, PD-L1 combination, and then the tumor of the T cell is not anymore energic, and will start to have its effector function and can kill the tumor cell. In adults, it was done in melanoma, and you see that after 36 months, overall survival was 58% for the combination, 52 only for PD-L1 and PD-1, and 34 for ipilimumab. So that's CTL4. It's very nice results in patients with stage 3 and 4 who nearly all died at that time. Ipilimumab was approved in 2010, and it showed survival benefit against standard chemo or peptide vaccination. And as you see the data here, 18% versus 5%. And the toxicity was colitis and also autoimmunity. Then nivolumab had also shown a few clinical trials, and it was done in adult tumors, non-small lung cancer, renal cancer, and melanoma. And also it showed very good results. And there is currently FDA approval for non-small lung cancer, melanoma, tumors caused by DNA repair disturbances, and relapsed Hodgkin lymphoma. And of course, also there is acute toxicity in skin rash, itching, diarrhea, and autoimmunity. And I'll come back to that later, to the toxicity. Immune checkpoint blockade works best in highly mutated tumors. And then it's a little bit a problem for children because they don't have highly mutated tumors. You need the formation of neoantigens, which you get when there is a high rate of mutation. What you could do is make the tumors more immunogenic. So that means you start with chemotherapy or radiotherapy, and that can cause a more immunogenic tumor microenvironment. And in that way, you can give immune checkpoint inhibitors and try to kill the tumor. CAR T cells, also very important, not so much in Hodgkin's disease, but still can be a possibility. CAR T cells are is a chimeric antigen receptor, and it has an antigen binding domain of an antibody, extracellular, plus also co-stimulatory domains, and these are intracellular. And you can bind 2 or 3 of those, of 1 or 2 of those co-stimulatory domains. It's expressed in autologous or allogeneic T cells, so of the patient itself or from donor T cells. Prerequisites, of course, for using these CAR T cells are expression of tumor-specific antigen on the tumor cells, and also expression of the antigen on the cell surface, of course. In July 2017 there was FDA approval, and it's nice that next to the BiTEs also the CAR Ts have been developed also in children. And so we didn't need first the adult studies, but we already had the pediatric studies too. And what is happening is that you take the T cells of a patient, use a viral vector to make them new antibody on the surface, so they will recognize the tumor cells, and then will grow in culture and give them back to the patient. Can we do that in children too, all those immunotherapy? We have a problem, of course. We have low patient numbers, at least also in Hodgkin's disease, in which you have patients which relapse only in maybe 15%, 10 to 15%. Tumors do not contain high amounts of neoantigens, which I already mentioned, and conventional treatment is fortunately very successful. So immune therapy is therefore difficult to test. Something else. I just show you a picture of an X-ray of an X-thorax of a 7-year-old girl, and I would like to ask you what you see on the picture. Of course, what you see here is the, oh, wait, I have to check the laser pointer. Do you see the laser pointer? Yeah, you see this. You see a central line. You're right. That's easy to see. Here you see a central line. What do you see more on the X-ray? Control L. Nou, dan moet het lukken. Yeah, I've got them back. Dus you see the central venous line, and you see also the line going there to the heart. What do you see more? Yeah, on this side you see this, and what do you think it is? That's right. Maybe another guess. Sorry, Yeah, it could be a lesion. Yeah, metastasis, of course. And when I would say it is a metastasis. And what kind of tumor it is, do you think? Do you know? But just looking to the picture, can you say just by looking on the X-ray what kind of tumor it is? What metastasis? Sorry? Could be a Wilms. What do you think at the back? You're pointing out. What do you think? Yeah? Yes. Great. Yeah, it's an osteosarcoma. She's missing an arm and her clavicula and scapula also. And she was diagnosed with an osteosarcoma. And unfortunately, during treatment, she broke her arm and we had to remove her arm and also the other part. And then a few months later, after stop treatment, she developed some metastasis and unfortunately a lot of metastasis. So we could not cure her, and we could not. Sometimes you can cure an osteosarcoma by just removing the metastasis, of course. But when both lungs were full of metastasis, we could not do it. So she died, unfortunately. But she still lives on because I take this picture with me and show it to everyone because it's a lot of. As I did in the beginning too, of course, you miss that there's something wrong because you only look to the X-ray, to the heart, to the lungs, and you're focused on the porticot and maybe a metastasis, and then you don't look also to the right above, and you miss the arm. Very, very good that you saw it. Okay, you all wake, and I have some slides which I will show you about the treatment of the lymphoma, and this just a lymphoma cell and a T cell, and there are a lot of new strategies available, and I will focus on two of them for the treatment. But you see here the monoclonal antibodies, as I showed you, rituximab. You see an ALK inhibitors here for the ALCL. You see the BiTEs here, and the CAR T cells here. But I will focus on those two, and that is. Yes, that is just the ADCs, which I mentioned already, brentuximab, and there are a lot more, of course, and also the immune checkpoint inhibitors. So, new strategies in Hodgkin treatment. I already mentioned the brentuximab vedotin, and it's already done in some studies in adults. And important trials, the Athera trial, published in The Lancet by Moskovich, in which they show that brentuximab was important during consolidation. So that means that was a better progression-free survival in patients who received brentuximab after consolidation treatment. And also in relapse treatment, they found that the BRAVE study, in which they combined brentuximab with DAP, so high-dose Ara-C, cisplatin, and dexamethasone, and they showed that they had a very high, before consolidation, high complete metabolic response. So two important studies which show that brentuximab has a role in treatment upfront and at relapse. And as you look in what did we do in pediatrics, and it's already published in the Lancet Hematology in 2018 by Locatelli and others, and they show that monotreatment of brentuximab in Hodgkin and ALCL has a real value in the treatment and for those patients. And what we see that and I show that here, that in Hodgkin's disease, an overall survival of 47% was found in the Hodgkin patient treated, and for ALCL it was even 53%. And the toxicity was mild and reversible. And also we did studies in pediatrics, and we had a study which was done by Monica Metzger in St. Jude. She replaced vincristine by the brentuximab, and she showed that in 77 patients who were included, 27 had a CMR, complete metabolic response, at the early response assessment, and they were spared radiation, of course. And all other patients received radiation only to the residual node. So that is different compared to the Euronet, where you have to radiate the whole lymphoma, what was found at diagnosis. And in this case, it was only radiation of the residual nodal tissue, which was found at ERA. And she had she showed that there was a event-free survival of 97%, and overall survival of 98%. Two other studies which use brentuximab in relapse setting, that's done by the group of Steve Daw, and shown in British Journal of Hematology, where he showed that brentuximab added to bendamustine treatment gives an overall survival, overall relapse rate of 83%, and an overall response rate, of 83%, and a complete metabolic response in 79% of patients before consolidation. And recently also Cole from the COG showed that brentuximab combined with gemcitabine gives a CR rate of 67%. So very nice results of brentuximab in combination with other treatment in pediatrics. The other strategy I want to discuss is the immune checkpoint inhibitors. And there's a study, it's nearly published. It's unfortunately just 2 weeks ago rejected by JCO. It's a study in which was done in Europe and in North America, where we had a study in which we combined nivolumab and brentuximab. So the brentuximab as ADC and nivolumab as a checkpoint inhibitor. And it shows very nice results in patients below 80 years. We had a complete metabolic response of 89% and an overall response rate of 98% before consolidation. And that was after 4 courses of nivolumab with brentuximab, and some, when they are not at that time in complete metabolic response, then they were then we added to brentuximab the bendamustine, which was shown by Steve Daw that it had good results. And toxicity was mild. So in intensification, you see there are some grade 3 to 4, but it was easily handleable. And when you look at the pediatrics and you focus more or less on the immune-related problems, then you see there still no grade 3 or 4 problems found in that study. Another study which is running at the moment, also in the COG and in the Euronet context, and that's pembrolizumab, which is already approved by the FDA or by the EMA for second relapses in children. And that study is a sort of upfront phase 2 study where patients can enter a diagnosis, and then only the slow early responders will be treated by pembrolizumab, and all other responders, so the rapid early responders, will get no pembrolizumab, but just COPDAC courses 4. And in the Euronet, we only treat those patients who have a treatment level 3, so the high-risk patients, and they will receive pembrolizumab. The only thing is that pembrolizumab will start at ERA, so when the COPDAC courses started, but after the COPDAC courses, you only need another 12 doses of 11 to 12 doses more of pembrolizumab, so that means another half a year of treatment. The results are not yet there. We have now an abstract sent to EHA and to the SIOP 2022 with some earlier results. Are there other drugs? There is a study coming that is a study in combination with nivolumab, and that's with a LAG-3 inhibitor. It's called relatlimab, and it's a study in which patients with a first or a relapse or refractory relapse can enter, but because we have a very good results at first relapse, probably only second relapse patients will enter, of course. but it's also a very nice, a promising drug which maybe can give less toxicity and best effective results. There are already available CD30 directed CAR T cells, so that could be also an option to use in Hodgkin cells because those cells are CD30 positive. There is an anti-drug conjugate of CD25, anti-CD25, and that's directed to the Hodgkin microenvironment, so that could be a possibility. And there is also an anti-CD37, which is widely overexpressed across tumor types, and also in Hodgkin, which can be an immune checkpoint inhibitor, which can be used also, but there are no studies yet, at least not in clinical studies. I mentioned earlier, I will come back with the immune-related toxicities. And of course, when you use new drugs, you can see the early toxicity is easy to encounter, but the late toxicity, as we know of the chemotherapy we have, so secondary malignancies or infertility or heart failure, we don't know anything about in those new drugs. And especially when you say, recognize that those drugs are immunotherapy, so you use the immune system to kill tumor cells. You can imagine when you activate the immune system that it can give autoimmunity problems. And that is also what is seen. Most of them are reversible, and sometimes you need corticosteroids to revise the problem you have at that time. But if you see what is mentioned nowadays in the literature, and it's a paper in 2020 and 2021, you see that there are a lot of dermatologic toxicity with CTLA4 and 30 to 40% with PD-L1, but most of them can be cured by topical corticosteroids or by steroids systemically or orally. Then you have the gastrointestinal problems, so diarrhea and colitis, which is also found very often, but less with the PD-1 and PD-L1, but more in the combination, of course. You have hepatitis, endocrinopathies, so steroid problems of pituitary problems. Although they are rare, it will be a real problem if you have them, of course. And what we see is pneumonitis. I've never seen it, but we have a patient, I think on the solid tumor, who had a pneumonitis, who was treated with nivolumab also. So it's a problem which can happen and you should be aware of. So that means also you should check the patients for this problem. So check for the thyroid, for the thyroid problems. And here I've show you a table which was published in 2020, in which they show the dermatological problems, how to diagnose it and how to manage it. And I will not go through that in detail, of course. But we have, for all the main problems you can find, they show how to work with and how to do it. And here you see the CTC-AE severity grade with 1 to 5, and it's also description how to set it, and the corticosteroids, what you can do, and also, of course, you need to discontinue the immunosuppressive therapy, so you have to stop with the drug you use, of course. In summary, new drugs are needed to replace the toxic drugs and or the radiotherapy, causing less lethal effects and higher survival rates. Monoclonal antibodies show promising results, and those results were found with rituximab in BNHL and also brentuximab vedotin as an antibody drug conjugate in Hodgkin lymphoma. The immune checkpoint inhibitors show to be important, especially in Hodgkin disease, as new drugs. But we have to be careful considering the late effects of the new drugs, and it will take some time to get those data. Is it possible to replace current chemotherapy courses with immunotherapy? It's a little bit too early, but maybe we try to do that. And at least what you see with pembrolizumab, which is added to the Euronet C2 trial. And then you can see that maybe D-COPDEC 21 is not necessary more. You only use pembrolizumab with COPDEC. That could be a solution. It's a challenge to incorporate new drugs in frontline studies in children due to outstanding results with current treatment. And it's also important to do phase 1-2 studies of promising drugs in children as early as possible. Just don't wait when you have the phase 3 trials already done in adults. And yesterday, Andy showed some nice cytomorphology pictures, and I have one for you. And this is the last question I ask you. What do you see here? What is that? What kind of cell is this? You can find them in the bone marrow. Sorry? No. These are most of the time somewhat smaller. It looks like a megakaryocyte, I think. Do you think too? But if that's the case, then you have probably a myelodysplastic syndrome because all those nuclei are separated from each other. We call this an osteoclast. Osteoclast. Sorry?
It's one of the biggest cells
Yeah,
in the bone marrow.
exactly.
You will not find it in every smear, but
Yeah.
sometimes it's
Yeah. So I'm also promoting cytomorphology and dish. Okay, questions?
Thanks a lot, Håkan. Especially that you were willing to give this talk twice, yesterday and today. Any questions from the audience?
Thank you. That was really interesting. The immune microenvironment seems like an interesting target in this disease. Is there a lot known about kind of the cytokine responses that are going on, and are there approaches being considered to target those? So I know in some other diseases, things like IL-6 you can target with tocilizumab and things like that. Is there similar things here?
I think so, but it's not that done in studies. But you're right, the microenvironment is, I think we can gain a lot just to attack the microenvironment because the Hodgkin cell is depending on it. The only problem is, of course, that you will kill then normal cells. And yeah, it could be that it's difficult. How much do you have to give of the drug, for instance, to kill the tumor cells and not to kill all other cells and give problems in the sense of autoimmunity, of infectious disease, because you kill your immune cells. But I think and that's why I mentioned TARC. Already there are some drugs which inhibit TARC. So that could be a possibility. If you inhibit TARC, then the Hodgkin cell cannot communicate anymore with its microenvironment, and then probably you have could be a cure. Yeah.
Thank you very much. Are there any considerations in choosing your immunotherapy treatment that might impact on subsequent treatment? So for example, in a very high-risk Hodgkin's, if you're thinking they may end up needing like an allogeneic stem cell transplant, would that influence which immunotherapy you may or may not choose?
Yeah, that's a good point. At the moment, it's difficult to give patients upfront immunotherapy, but in the near future, I think it would be great to have them on the shelf and that you can say, yeah, you individualize your treatment and you say, okay, in those patients, and I show you in one of the first slides, what we see is that patients who have a Deauville 5 at ERA, those patients do worse. So maybe what you can do is if you have those patients, then you can enter, as we do with leukemia treatment, for instance, you add blinatumomab or inotuzumab, then you can say, okay, in the Hodgkin disease, after ERA and they have a Deauville 5, maybe you then will add pembrolizumab, for instance, and give them a better result of survival.
We've been talking about the late effects of new treatments quite a lot these past 2 days, and you finally have a disease where patients survive after phase 1-2 trials. Do you collect the late effects for like 10, 20 years? Do you have such a program in place?
No, it's not really in place. I think we do it in the Maxima because we have a very good late effect follow-up, more or less, so we can do it ourselves, but it's not yet done. And I'm not sure if it's already arranged within SIOP or within the adult treatments facility, if it is a possibility, because I think it's so important to know, because these are very promising drugs. Just for example, I had a patient who was treated with chemotherapy and had a very terrible time. He played volleyball on a high level and could not do anything anymore. And because the study was at that time open, where we combined nivolumab with brentuximab, so he started with that study. And when he was finished, he said he was another boy. And not only when he finished, but when started, and later on he told me that. He said, now, it's the treatment you should give up front and not at relapse, because he had any toxicity. So I think there is a place for the drugs, but still the late effects are very important. So we need to know them before we could start this treatment. But I think there is a role for the new drugs.
But also convince the pharmaceutical companies, I think, if you have a new trial, that they need this, because it will be asked, I think, when they try to register, to have this data available.
Well, it will be registered, especially also nivolumab with BMS. They are doing, because when I just give the patient who relapsed still the study treatment, and we have to give them the results and the follow-up. Yeah. Please.
I hope that we optimally will have late effects people involved when new trials are designed. So we fix late effects endpoints that can be then followed 5 or 6 or 7 years after the trial ends, and the primary treatment people move on to the next trial. And that should be a system whereby that can be inherited by late effects organizations or groups, so that you have it already set up and we don't lose that information. We can collect it prospectively and not go back and do retrospective studies, which are time-consuming, expensive, and often difficult to perform.
Yeah, exactly, not reliable. No, you're right. But that's a real struggle, and maybe 5-6 years is okay, but we need 20 years to follow up.
Okay, may I ask you the last question? I asked you yesterday, so we had 24 hours to come up with the perfect idea. What do you envision concerning these new drugs? That they replace single drugs in our primary treatment, whether they will replace complete blocks, or they will be given on the top of our current blocks, because WEPA and Decoptac are still toxic.
Yeah. No, it's a very good point, and it's difficult to answer that. What we are now doing is adding pembrolizumab on Copdac, but that's already replacing etoposide and doxorubicin, of course. So if you compare it with Decoptac, I think that's a real step forward, more or less. But yeah, what I mentioned already, and I listened to my patient, he said you should start up front with the drugs and not give us chemotherapy where we'll be very tired, toxicity, toxic death, we discussed with the Decoptac. That's not what we want. But it's rather difficult. We have to show more data, that it's feasible, that it's cheaper, of course, because it's in the study. Then it's doable, but when it's not in the study, nivolumab or brentuximab are very expensive. So we are lucky in the Netherlands that brentuximab we can get it. So that makes that it's available for us, but for a lot of countries it's not. So they have to stick to chemotherapy. But we need a lot of data, and I foresee that it will change, but maybe in 15 years.
Okay, thanks a lot. Thanks for being here for the first 4 working groups. We will now have lunch, and then we'll meet for the next 4 working groups and see what happens to our patient.